Number 20 here is actually a fairly simple problem. It might not seem simple when you look at it, but it's fairly simple. Part A says find a function phi such that its gradient is f. First of all, how do you know there is such a function phi? Check and see if it's conservative. How do you do that? There's your m, there's your n. Quickest way is to use the scalar curl. It's nx minus my, the partial of the second component with respect to the first variable, minus the partial of the first component with respect to the second variable. 0 minus 0 is always 0 in this example. And remember, there's a theorem that says when the scalar curl is 0 and the domain is simply connected, no holes in it, the vector field will be conservative. There will be a potential function. We will have success in finding phi. In fact, the way this problem is phrased, you don't have to compute the scalar curl. You can just look at it and guess what phi is. 4x is the derivative of phi with respect to x, and y squared is the derivative of phi with respect to y. Combine those two equations, essentially integrate them to get 2x squared plus 1/3 y cubed plus c. It's fine if you want to do plus c, but you don't have to. We're just after one function, one potential function. We can use c equals 0. So effectively, I just did a couple integrations in my head there. Sometimes it's a little trickier if x and y are being multiplied. You'd want to write the integral sign and be careful about it. I did at least one example like that. I don't remember what day. The book does at least one example like that. But in this example, it's fairly straightforward. There's your phi. There is your potential function. The gradient of phi, if you want to check it, is 4x comma y squared just by differentiation. And that is the given vector field. So that means this vector field is conservative. That's what conservative means. It is the gradient of some function. There is a potential function. I've said this before, I'll say it again. Most vector fields don't have a potential function. Most vector fields are not conservative. They are not gradients of some function. It's only when the scalar curl is 0 that they are. That's pretty rare. Second part of the problem says, let C be any oriented curve beginning at the point 1,4 and ending at the point 0,6. Compute the line integral. And it's supposed to be an easy problem. Why is that easy? What do? I don't have to parameterize the curve. Fundamental theorem of line integrals, which applies to conservative vector fields. F is a vector field whose components are continuous on a connected domain or in space. A and B are any points in D. Conservative means there's a potential function. If it's conservative, you can do the line integral by just doing a subtraction. No need to parameterize the curve. The potential function evaluated at the endpoint minus the potential function evaluated at the starting point. So starting point is 1,4, ending point is 0,6. Using our notation with dr instead of ds, this will be phi of 0,6 minus phi of, what was it? 1,4. In the book, they use the letter F. Here I'm using phi. It's not the spherical coordinate phi. Okay, I'm using a different version of phi here instead of that. Use this function now from part A. Phi of 0,6 is going to be 0 plus 6 cubed over 3. 6 cubed is what, 216, I think? Yep, 216 divided by 3, which will be 72, minus phi of 1,4, that'll be 2 plus 4 cubed is 64, divided by 3. This will be 70 minus 64 thirds. 210 minus 64 over 3. 46 over 3? Should be like a 48.6, I think, repeating. That'll be the line. You should be able to check it by parameterization if I ask you to. For this example, what's a parameterization of the line from 1,4 to 0,6? 1,4 to 0,6, that line right there. X goes from 1 down to 0. Say as t goes from 0 to 1. So I can use 1 minus t for x. Y goes from 4 up to 6. As t goes from 0 to 1. So I can use 4 plus 2t. Just did that in my head. That's worth practicing. Those are two quantities. The x going from 1 to 0 as t goes from 0 to 1. And the y going from 4 to 6 as t goes from 0 to 1. Just computed those in my head. The vector field is 4x comma y squared. So I'd be computing the function I would integrate would be f of r of t dotted with r prime of t. That would be the function integrate by hand as t goes from 0 to 1. So when I integrate that from 0 to 1, I should hopefully get 146 over 3. Yeah. Any other parameterization, if you do it right, should give you the same answer. What's the meaning? Why do we get a positive answer here? This gets to the meaning of line integrals. There's the vector field scaled down. It's really a direction field. Lighter vectors are really longer. Darker ones are shorter. Maybe I want to see the parametric curve in there as well. 1 minus t, 4 plus 2t. T goes from 0 to 1. There it is. It's oriented from the bottom point to the top point. The velocity vector for this is going to be pointing in this direction to the northwest here. Notice that generally speaking, that velocity vector and the corresponding unit tangent vector are generally speaking in the same direction as the vector field. So if you think of the line integral in terms of a dot product, f dot t ds, those dot products all give positive contributions to the integral. That's why we get a positive answer as opposed to a negative answer. Which makes me want to wrap up by going back to page 1 of the exam and saying, like, well, what kind of problems did I have, like at the bottom of page 1? Which vector field is definitely not conservative? I think, if I recall correctly, one of the pictures, there were two pictures of two vector fields shown here. One of them had arrows circulating around the origin. A vector field like that definitely cannot be conservative. Why not? Because if you integrate around any circle centered at the origin, if it were conservative, it would be independent of path. Your starting and ending point would be the same thing. You got to get an integral of 0. But you can't get an integral of 0 because the tangent vectors are all pointing in the same direction as the vector field. You get positive contributions to the integral, you'd have to get a positive integral. Which also reminds me of Green's theorem. We should glance at that quick. That was back in the last page again. Use Green's theorem to write this as a double integral. What would it be? What does Green's theorem say? It says a line integral like this would be equal to a double integral of the curl, the scalar curl for a two-dimensional vector field. Nx minus my. Nx here you can see is going to be 2x plus 1. Right? The derivative of n with respect to x there. Going to be 2x plus 1. My is going to be 0. You're going to be integrating 2x plus 1, a double integral of 2x plus 1 over a disk. C is the unit circle oriented counterclockwise. Green's theorem is stated in terms of a counterclockwise orientation to your closed curve, where the region is inside the curve to your left as you go around. It'd be a double integral of the scalar curl. So part A was to write that double integral down, and part B was to use polar coordinates to compute it. It's over a disk, the unit circle. Polar coordinates is definitely the best thing to use there.